Yes, good evening all. Now we'll go for the next chapter, that is digital control systems. Okay. See, now when we are talking about digital control systems, the very important thing is we are having all data that is there in the analog terms, that is, it is continuous one, but the need is there that it should be discretized or digitized, right? And that's why to handle that digital data, see, because digital data is having its own advantage, we know the disadvantage also. Continuous signals are more accurate compared with the digital signals, but handling of digital signals is more easy compared with the analog signals. Like nowadays you'll find all your PLC or DCS or SCADA, all these systems, what they are using, actually the controlling system is digital one, right? And that's why you will find digital systems, so some advantages are there, right? And that's why we should understand, if the we should try to learn, if the data is digitized, then how it can be controlled. Okay, so first point related with that is, what are the advantages of digital system over continuous system, or continuous signals rather. Advantages of digital control system over continuous control system. So number one, very important advantage is the accuracy, first thing. See, even if the analog signals are very accurate, we are not having equipment or instrument which can measure those accurate signals, right? In analog terms. But if you talk about digital one, you will find yes, because the signal which you are having, right, they are represented in zeros and ones, and might be typically 12 bit or more than that. For a single number we are having very small error which is coming, that also can be detected, right? So I'll write in short, 12 bit or more for a single number, right? And therefore small errors also can be detected. This is one important advantage. Then the second one is, implementation of errors is also easy in digital systems. In digital mode, addition, subtraction, or different operations, right, comparatively it is easy to handle, and that's why the implementation of errors also becomes easy. So I'll write implementation of error is easy. Okay. Then the third advantage for this is flexibility. Analog controller is difficult to modify or redesign once the hardware of that is implemented, right? But digital control system, even if it is what it is a software, right? For modification, it is not that we are changing any hardware, just we have to change the software, and yes, it will be possible for us to change the system is the controlling system, and that's why you will find flexibility is very good. because modification is easy. See, all these things in detail are given in the notes, right? So definitely I am, in short, I'm writing it over here just for you to understand what we are trying to talk about. Then the next thing is speed of response. Okay, the processing speed, because of digital systems, it increases, and even if the signals are there with high frequency, that also can be sensed very easily, because speed is more, even if the frequency of the signal is high, will be possible for the system to act on that, right? So I'll write processing speed increases, so signals with high frequency can be sensed. ठीक है. Then the next point is E, that is cost of the system. Yes, all of you are aware of digital systems nowadays. Cost is becoming less and less. Why? Because of the VLSI, and a very large scale integration is possible, and because of that manufacturing is better, faster, and more reliable integrated circuits we can have. And for digital circuitry, as soon as more and more R&D is there, you will find their size goes on reducing, and that's why, because of that, the price also. So cost is less, and with VLSI still decreasing. Okay, so these are some of the advantages of digital control system, and that's why we should think of, I mean, why we are using digital systems, right? These are some of the reasons. Then the next point related to this is second one. What is the structure of digital control system? So I'll write structure of okay. So your regular, how it is different from the analog system. So first I would like to draw for analog system, and then I'll slightly modify it so that it will be your digital system, right? So analog system many a times we have learned, right? Yes, what you used to have, yes, process is there, then the controller is there, comparison you are going to have, in the feedback you are having your sensor, right? Many a times we had drawn this block diagram. So input given, error you are having, going to the controller, final control element, and your process output available, sensed back, given to the sensor, and from sensor back feedback will be there for comparison, right? So I'll write input, feedback, controller, process, output, sensor. Correct? So this is your analog system. Now if you are talking about digital system, of course I forgot to write over here is control system only. So what it is, yes, see, your process cannot be digitized, right? So process is analog, the simple process which you handle, uh, and the one who is going to control is actually your computer, right? So computer, whatever will be the output of the computer will be digital one, so should be converted into that digital output should be converted into analog output. So you should have DAC over here. Then whatever will be the output, yes, given to the sensor, again your sensor is analog one, but you want to give signal to your computer, so it should be discretized and then will be given back to the controller. Now means what? Again I'll draw it, have patience. Yeah, and I'm giving this thing to the computer. Now instead of a controller, you are having some computer, might be your PLC, might be DCS, might be SCADA, anything which is handling the signal digitally, right? So you are giving input, yes, you are giving input to the computer, correct? Output of that will be digital signal, you want to give it to your process. So that means this should be converted into analog signal, so you should have DAC over here, digital to analog converter. Now this output is of course analog one, which will be sensed by your sensor, correct? Then this sense signal will be also analog one, correct? But you want to give it to computer, so you should have ADC over here. So on simple line, these two blocks definitely we are supposed to add in the system, so that it will become your digital control system. Okay. Now third point, first we had seen advantages, then what is the structure, then see, you're having ADC, means what? How you are converting analog signal into digital signal, right? That is called as process of sampling. Sampling is done over here. Sampling is done means the signals are converted into analog, into digital using sampling. You might have learned this thing in your second year, right, in the digital electronics subject. So just I'm trying to throw some light on that, right? Yeah. So what you are having? You are having your signal continuous one. Now what is important for us over here is not the how it is digitized, because I know whatever variables that we are going to use will require it for writing mathematically all these digital signals, right, and handling these digital signals in control system. That is important for us. So let us say I am saying it is x of t, which is your continuous signal. Continuous signal. Fine. That signal is sampled, so sometimes this switch will be on, this switch will be off, right? And the time period that you are giving for that, let us say t, every after capital T time, this will be on and the signal will be given, so it is getting converted into pulses, zeros and ones, right? So sampling time, let us say t. Capital T. Okay. And what you are going to get at the output side? Yes, it is going to be digital signal. And this digital signal, now how we are representing? X star t, correct? Now we'll see how mathematically we can put all these things. जैसे हमने we did it for continuous signal, we had Laplace transform and all those things, and we tried to write the thing right in S domain on the same line what it should be, right, to convert this signal, digital signal, which is for which you are in time domain. Now how we can go in frequency domain and can handle these signals, right? So the next thing comes very important, and that is Z transform. Now first thing, what is this Z transform, right? You know now Laplace transform. On the same line I am writing something related to that, and that is Z transform. So what is this? So keep in your mind Laplace transform. When we are writing, I'll write it over here. Why I am starting with Laplace transform? Because you know Laplace transform and your variable over there was S. Correct? Your variable in time domain, it was t. When you had taken Laplace transform, you were in frequency domain, and we said the variable becomes s. Should I write it over there? Wait. Variable s. Right. Okay. So what Laplace transform does? It converts a continuous signal in time domain to the continuous signal in frequency domain. So in short, I'll write converts continuous signal in time domain to continuous signal in frequency domain. Fine, clear bhi to yes, definitely we know this, right? S transform or Laplace transform, what it does, whatever was the continuous signal in time domain, it is converting that signal into, that is continuous signal only, but in the frequency domain. On the same line, when you are talking about Z transform, where your variable is going to be Z, variable is Z. Okay, and what it is doing, it is converting discrete signal in time domain, or digital signal in time domain into digital signal or discrete signal in frequency domain. So yes, very well we can say these two things are very much parallel. Whatever your Laplace transform is doing in analog systems, right, same thing is your Z transform is going to do for the digital systems, right? Now Laplace transform expression of the systems with digital signals containing exponential terms in the form of e raised to st, and which makes the manipulation in the Laplace domain slightly difficult, है ना? We know that. What do you mean by Laplace transform? Your signal multiplied by e raised to minus st you are having, and you integrate all those things, and a definition of your Laplace transform. I'll not go into details of that because I don't want to waste time on that now, right? So Laplace transform expressions of the systems with digital signals containing exponential terms in the form of e raised to st, right? This e raised to st, this term is going to make the Laplace domain difficult. So what is going to happen? Let us see. That means, see, I'll write, if the output is sampled, right? If output of the, after sampling, whatever is the output, that is output of the sampler, we are denoting it by x star of t. Correct? So this x star of t, if I want to take Laplace of this, what it is going to be? Laplace of x star of t. So how we are supposed to write this? We are supposed to, let us say we are writing x star of s. We are in s domain only. We are talking about taking Laplace of the digital system, and what is going to happen because of this. Whenever you are talking about digital system, you are doing summation, right? In analog signals you do integration on the same line. In digital signals you are supposed to do summation. You cannot integrate, so it is summation. Summation for, let us say, k equal to 0 to infinity, n number of samples you are having. So k number of samples you are having rather. Okay, your signal x, right? And at every instant your t is changing. So let us say it is k into t, because your sample time is t. So 1, 2, 3, 4 pulses. So it will be t, 2t, 3t. That will be your time now. I think all of you are, you will be able to understand this, right? This is t, this is continuous. Over here it is t time interval after which the sampling is done. So sampling time is t. So it is going to be t, then 2t, 3t, 4t, 5t. So that will be the value of t. So how I can generalize it? I will say k. K is changing from 0 to infinity, right? And what you do? E raised to minus ts or st we used to write in Laplace domain. Correct? I think if I'll write x of t ka Laplace, you know that it is integration 0 to infinity your x of t e raised to minus st dt. This is definition of Laplace. Same thing we are trying to write it for a digital system, right? So digital system ke liye when you are writing Laplace of x star of t, which you used to represent is as x of s, right? So I am writing x star of s. It will not be integration, it will be summation. Your signal at that particular time e raised to minus st, but your t is what? Kt. So it will be e raised to kts. Correct? Right? Now this e raised to minus kts is not a rational function of s, right? So other than a multiplying factor, and it creates difficulties. So this e raised to minus kts is not a rational number of rational function of s, which is creating a problem for us, difficulties for us when we are going to inverse the function. So that's why what we are going to do is, for this e raised to kt, we'll substitute something. And what we are going to substitute, I'll tell you. I think no need to have Laplace ka definition. You know very well. No need to write everything, and then it may confuse you. So as e raised to, I'll just in short I'll write e raised to minus kts is not a rational function of s. It will become difficult to handle, right? So what we are doing now, we'll substitute. Let z is equal to e raised to ts or st. So very important thing I had written over here. Instead of writing some exponential term, e raised to, k to constant hai, so no need to worry, minus also no need to worry, st, e raised to st, we'll say it is z. So while taking reversing, z inverse, right, it will become easy for us to take the inverse, right? So what you are going to have, e raised to minus kts, which is equal to e raised to st raised to, let us say, k minus k, which will be z raised to minus k. So we'll substitute over here. So what you are going to have, x star of s will denote it by now z we have introduced. So I'll write z x of z now, because your variable is not s now, it is becoming z, that's why. So will be equal to summation of k equal to 0 to infinity, correct, x kt and z raised to minus k. Okay, so Laplace of Laplace nahi. So z transform of x of t, whenever you are writing z transform, be this z capital, whenever it will be a variable for you, correct, you are going to write it as small z. But when you are writing, see, Laplace ke liye we used to write L, so it is totally different from s, so no need to worry. But over here z transform, this is the normal way to represent, so we cannot change the way, right? Whatever the way is there, we have to follow. So when you say Laplace of x of t, right, you write this L capital and then you write x of s. On the same line, when I'm saying I'm taking z transform of x of t is equal to x of z. Now this variable definitely small, x of z, which is equal to summation of k equal to 0 to infinity, correct, x of kt into z raised to minus k. This is a representation, this is your variable. So very important thing we had seen, what is the definition of z transform. So I'll make a bracket for it, correct. Now again, this x of t, we are not going to write it as it is. How to write this thing, I'll tell you. What is the meaning of that also, I'll tell you. Let me save this, yeah, and I'll clear the board. Yes, now the next thing, again, when you are writing we are going towards the simplest format for writing, representing your z transform. Okay, so how we can write now, x of z, right, means x function ka z transform. Okay, how you can write, yes, z transform of x of t, correct, is equal to, yes, z transform of x of kt, right, yes, because your t is k into t, which is equal to summation of k is equal to 0 to infinity, correct, x of kt into what we had seen, z raised to minus k, right. Now this x of z is equal to this. Once more I can write the same thing as summation of k is equal to 0 infinity. See, now this thing is telling you x ka value at kt time, correct. Instead of that, we can say first pulse के लिए what is the value, second pulse के लिए what is the value, third pulse के लिए signal का जो भी value with respect to time, correct. All these this is your digital signal, right, and you are saying k is equal to 0 or rather 1, ये 0th है, 1, second, third, fourth. So these values, so instead of writing in terms of time, we'll write it in terms of the instances, and I can say the instantaneous value for that particular number of instance, we can represent it as xk, x of k. Always square bracket means nth or kth instant ka value. Okay, instead of talking in terms of time, we are talking in terms of instances. Fine, it is one and the same. First instance, second, third, fourth, and what is that instantaneous value? Z minus k. This is your z transform. Again, I'll make bracket for this, very important, and we are going to follow this format. Fine. Now the next thing is, some standard signals are there for which we want to get the value of Z transform. So we'll see what are those things, right? Yeah. So next point is fifth point, I think. That is Z transform of standard discrete signals Okay, number one.